Okay, so we're going to start this video off by talking about order of magnitude. Now, order of magnitude is typically something that is brought up when the actual value of something doesn't really matter, and we just want a ballpark figure. When we talk about order of magnitude of a number, we're talking about the closest power of 10 for that number. So, here's a simple example. An apple has a mass of 120 grams. The closest power of 10 for that is 10 to the power 2, which is 100. Therefore, we can say that an apple's mass has an order of magnitude of 10 to the 2. Now, I say here that the mass of an apple is 120 grams. Well, is that true for every apple? No, of course not. I mean, you could have an apple with a mass of 80 grams, a mass of 200 grams, but if you think of, what is a reasonable mass of an apple? 70 grams, 80 grams, 120 grams, 200 grams, maybe if it's a giant apple. And if you think of the different orders of magnitude, remember, we're talking about the closest power of 10. 10 to the 0 is 1. 10 to the 1 is 10. 10 to the 100, 10 to the 2 is 100. Let me erase that. Okay, and if you look at the numbers, 70, 80, 120, 200, what are they all closest to? Are they closest to 10? Are they closest to 100? Are they closest to 1,000? I would say they're all pretty close to 100, and therefore we can say that the mass of an apple has an order of magnitude of about 10 to the power 2 without, talking about one specific apple. In other words, apples in general have a mass of about 10 to the power 2 grams. Okay, and so order of magnitude, again, is an estimation tool that you can use when the actual value doesn't really matter, that you just want a ballpark figure. Okay, so let's look at some examples of that. By the way, as we're going through, please make sure you're pausing and adding these things to your notes. Please use good note-taking skills. You want to write as quickly as you can, but please do not feel compelled to write every single word. Only write the important information. Now you might ask, how do I know which information is important? Well, that's part of note-taking skills, is looking at the slide and figuring out on your own what information is the most important information to write down on the slide. Alright, so I said that before, order of magnitude is used if a precise value is not needed, closest power of 10. Here are some examples of different orders of magnitude in the universe. Now, you do not need to know any of these, or I should say you don't need to have memorized any of them, although it would be helpful, I suppose, if you did. But this is just to give you a ballpark figure. Okay, so when it says, for example, that the age of the universe is 10 to the 18 seconds, does that mean that the age of the universe is literally 10 to the power 18 seconds? No, of course not. It's just that the age of the universe is, somewhere between 13 and 14 billion years old. And if you convert that time to from years to seconds, it's somewhere around 10 to the 18. Okay. Same thing with the speed of light, 10 to the 8 meters per second. Now the speed of light is not exactly 10 to the power 8. That would be 100 million meters per second. It's actually about 300 million meters per second. But again, for the purpose of just giving like a ballpark estimation, 10 to the 8 is fine. And you can use these orders of magnitude to very quickly make estimates and see the differences between different values. So for example, if you look at the mass of the proton versus the mass of the electron, 10 to the negative 27 and 10 to the negative 31, what is the difference between those two orders of magnitude? Well, hopefully you realize the difference between negative 27 and negative 31 is a difference of 4. In other words, I can say that the mass of the proton is about, the mass of the proton is about 10 to the power 4 times bigger than the mass of the electron. Okay, that's about 100,000 times bigger. Now, is that exact? No. Okay, but that's just to give you an estimate that, hey, the mass of the proton is way, way, way more than the mass of the electron. Okay, so again, order of magnitude is just an estimation tool. Okay, so pause it there if you want to look at that some more. We can do some simple examples. This example just says find the difference in order of magnitude of the mass of the universe to the mass of a quark. If you ask what is a quark, that's a good question, but we'll talk about that in IB Physics 2 next year, okay, so that's not something you need to worry about right now. But if you go back to this chart here and you look at the mass of the universe and the mass of the quark, at least their orders of magnitude, 10 to the power 50 and 10 to the power negative 30, that's a difference of 80. Okay, so you can say that the difference in order of magnitude is 10 to the 80. In other words, 80 orders of magnitude. And just going through some other examples really quickly, I don't want to spend too much time on this because it's a pretty simple concept, order of magnitude. And you typically on the IB exam only see maybe 1 or 2 questions related to order of magnitude. Okay, so I don't want to harp on it too much. But this one says New York and LA are separated by about 3,000 miles and 3 time zones. What is the circumference of Earth? And you might say, how would you figure out the circumference of Earth just knowing that? Well, here, if you read through the work that's on the slide, you can see what they did. They basically said, okay, so 3,000 miles is 3 time zones. That means 1 time zone is about 1,000 miles. Okay, there's 24 hours in a day. Earth rotates once each day, and that would mean that there's 24 time zones on Earth. Okay, 24 time zones, each one is 1,000 miles. That means the Earth is about 24,000 miles around. Okay, estimation. That's an important skill to use in physics. Now, is the circumference of Earth actually 24,000 miles? No, it's actually more like 25,000 miles, something like that. So it's not perfect, but it's a really quick estimation that we just did. Okay, so considering that estimation took like 10 seconds, that's pretty accurate. See if you can figure out this one on your own. Okay, so it says the number of heartbeats of a person at rest in 1 hour to the nearest order of magnitude is what? Okay, now this is a multiple choice question. This question actually comes from a previous IB exam. So see if you can answer this question. Do you think it's A, B, C, or D? Okay, so hopefully you picked the answer as C. Now keep in mind this is an estimation question. You might have asked, I don't know how many heartbeats a person has in 1 hour. And that's fine if you don't know the exact number, but you should have an idea of where it is. You should realize that, okay, in 1 minute, a person at rest, their heartbeat probably beats somewhere between, I don't know, 40 to 80 beats per minute. Okay, so let's say if you chose, I don't know, 40 beats per minute, and there's 60 minutes in 1 hour, that would be 2,400 beats. Now, what if you didn't get 40 beats per minute? What if you're, I don't know, you're sick and, you know, your heart is beating at 100 times per minute. Okay, so let's say 100 beats per minute times 60 minutes. That would be 6,000. Now, the order of magnitude of both of these numbers is 10 to the power 3, because 10 to the power 3 is 1,000. And both of these numbers are closer to 1,000 than they are to, you know, 100 or to 10,000 or anything like that. Now, I guess you could argue that, you know, maybe 6,000 is closer to 10,000 than 1,000. But if you look at the answer choices, none of these answer choices are 10,000. Okay, the one that's closest is C. Okay, and so typically the IB tries not to give you ambiguous questions. Okay, if you had said, you know, maybe 10,000, then I can understand if you got confused if that was one of the answer choices, but it's not. Okay, so hopefully you got the answer C. Okay, pause it there if you need to look at some more. And just one more quick order of magnitude question. See if you can figure this out. What is the order of magnitude for the height of an average adult human in meters? Now, you might not know what a meter is. A meter is a little more than a yard. Okay, so see if you can figure that out. What is the order of magnitude for the height of an average adult human in meters? Okay, so the answer to this question is 10 to the power 0. Now, I personally am 5'8". I know some people are really short, maybe, you know, below 4 feet. Some people are really tall. I would say really tall, like really tall would be like, you know, 6 feet or more. Okay, so if you're 3 feet, 3 feet is not equal to 1 meter, but it's close. So if you say 3 feet is about 1 meter, and 6 feet is about 2 meters, and again, it's not equal. It's pretty close, but it's not exactly. I mean, maybe if there was a giant person, they might be 9 feet tall. I don't know if that's possible. But 1, 2, and 3 are both closest to 10 to the power 0, which is 1. Okay, 10 to the power 1 would be 10. Okay, and there's no average adult humans out there that have a height of 10 meters or 90 feet or sorry 30 feet. That would be pretty crazy. Okay, so hopefully you got that. Pause it there. If you have any questions, let me know. Okay, so now that we've kind of touched on order of magnitude, let's get into the SI system of units. Okay, pause it here if you need to add this to your notes, which you should be adding this to your notes. Okay, so in science, we typically use a system of units called the SI system. Okay, SI basically stands for International System of Units in French. You also might have heard this as like the metric system. Okay, now the reason that we in science use the SI system of units is basically for consistency purposes. That way, if I'm doing an experiment in the United States and I write a paper and somebody in Japan reads my paper and they're looking at the numbers in a completely different language, at least that part is consistency, or is consistent. At least the values are consistent, and so everybody's on the same page as far as publishing data and stuff like that. Okay, so units are really important, and it's really important that we have a consistent set of units in science, because some countries use different unit systems. Like here in the United States, we use the English system of units, like feet and inches and stuff like that. In Europe, they use the metric system, right? Kilometers, meters, stuff like that. Okay, so from country to country, in the general population, different countries might use different systems of units. But in science, in the scientific and engineering communities across the world, we typically always use the SI system of units. Okay, now, if you want to know more about what that means, what does that entail, the SI system of units? Basically, it all comes down to this. And if you want to take a picture of this or add this to your notes, that would be fine. But there's the SI in the SI system of units, there's what's called fundamental units. And so everything in the universe that can be measured, it can either be measured in one of these units or some combination of these units. Okay, so these are the 7 SI fundamental units, also called the 7 SI base units. And they are, for length, we measure length in meters. Okay, and for meters, we write a lowercase m. Time, we measure in seconds with a lowercase s. Mass, the SI unit for mass is the kilogram. Now in chemistry class, you probably use the gram. The reason for using the gram in chemistry is because when you're dealing with chemicals, if you were to do an experiment with a couple pounds of chemicals all mixed together, that would probably be pretty bad. And so you're probably used to using grams and working with grams in chemistry, but that is technically not the SI unit for mass. It's actually the kilogram. Temperature, the SI unit is Kelvin. We give that a capital K because it's named after a guy whose name was Kelvin. Electric current has the unit of the ampere with a capital A because it's named after a guy whose name was Ampere. Luminous intensity, which you will never ever see in this class, is measured in candela. That one's not really important. I will be honest, even as a physics major, I don't even think I ever saw that even in college. Okay, so that's not really that crucial, but all the other ones you will definitely see throughout IB physics. Okay, amount of a substance. I know everybody who's taken chemistry before has worked a lot with this unit. This is one of the SI units. One of the fundamental SI units. Amount of substance is measured in moles. Okay, so if you've ever worked with moles in chemistry, then you've worked with one of the SI base units. Okay, so everything that we can measure is either measured in one of these units or some combination of these units. Okay, and we'll talk about that in just a moment. We'll come back to this. Just really quickly though, I want you to pause here and read through what it says on this slide. And then I want to know what are your takeaways from reading this little article here. Okay, so take a minute to compose your thoughts and then we will move on. Okay, so we've talked about the 7 fundamental units in the SI system. I will say before I talk about derived units that the meter, second, kilogram, Kelvin, and mole we will see this year in IB Physics 1. We will not see the candela at all, ever. This one we will see in IB Physics 2. Okay, the ampere when we talk about electricity and stuff like that. Okay, so most of these units we will definitely see sometime this year. Just letting you know. That includes moles. Okay, so those are the 7 base units, or the 7 fundamental units. Everything that can be measured, and I said this before, is either measured in one of those units or in some combination of those units. Okay, now if you're talking about a physical quantity that's measured in combination of those units, that is what is called a derived unit. Here's an example. Speed. Speed is measured in meters per second. Okay, so the unit for speed is the meter per second. That is a combination of SI fundamental units. Therefore, meters per second is a derived unit. Okay, because it's not one of those 7 base units, it's derived from those base units. Okay, so this is very simple. All units in science, or I should say all units in this class anyway, are either measured in base units or measured in derived units. When we talk about things like, acceleration, that's measured in meters per second squared. When we talk about force, force is measured in newtons. We'll talk about this later, but you can write a newton as 1 kilogram meter per second squared. Okay, that is a combination of those 7 base units. Okay, so these are both examples of derived units. Alright, pause it there if you need to look at that some more. And there's one more thing I want to talk about in this video. Okay, and that is IB notation. Now, the IB uses a notation for units that you're probably not familiar with. Okay, here's how it works. Instead of using a slash to represent per, we use negative exponents. Now, let me break that down. First of all, when I say per, when something is being divided, you read that as per. So for example, if I say, I don't know, I make $15 per day. If I wrote this, everybody would recognize that this means $15 per day, and they would read that slash as a per. Just like if I wrote, meters per second, meters divided by second, it's understood that that means meters per second. So that division sign represents per. The unit being on the bottom of the fraction, you read that as per. Now in the IB system, instead of writing meters per second like this, we write it with negative exponents. Now, if you don't know what a negative exponent is, basically, if something has a negative exponent, for example, x to the power negative 2, that is equal to 1 over x to the power 2. So if something has a negative exponent, that means that quantity is on the bottom. So what I'm saying is, in the IB notation, you wouldn't write meters per second like this, you would write it like this. S to the power negative 1. Okay, so meters, and then per, it's per because if it has a negative exponent, that means you're dividing by it, per second. Here's another example, meters per second squared. This is how you would write in AP Physics. In IB Physics, we use negative exponents. We would write that like this, meters per second squared. Just like that. If I make $15 per day and I want to write that in IB notation, I would write $15 day to the power negative 1. Okay, and so that is the IB, or the European way of writing units. I never ever saw that in college. That's completely a European thing. It's not like a, more advanced way of doing it. It's just a different way of writing it. I'm not really sure why they do it, but that is how units are written in IB Physics. Okay, so please get used to seeing that. And make sure you understand how to read units in this notation. If I ask you, what does this say, and you're like, ms to the power negative 1, that's not the right way to say that. you should be saying meters per second squared. Okay, so make sure that you understand how to read this type of notation. Okay, pause it there if you need to look at that some more. Okay, so before we end this video, this is basically just an example of what we just talked about. If a car's speed is measured as 40 kilometers per hour, in IB notation, you would write that as 40. The kilometers is on top, the hours is on the bottom, and so you would write hours to the power -1. Okay, so there you go. Now, we're just going to do 2 more examples, and then we will be done with this video. So, here is an example. Which one of the following is a fundamental unit? Now, in this case, the answer is already given to you. Sorry about that. But let's say the answer was not given to you. There's a very easy way to tell the answer to this question. Okay, and that's by knowing the 7 SI base units, the 7 SI fundamental units. If it's one of those 7, then it's a fundamental unit. If it's not one of those 7, it's a derived unit. So we have kilo, ohm, and volt. Some of those you might have heard of, some of them you probably haven't. But if you've never heard of it before, that means it's probably not a fundamental unit. It's probably a derived unit. Okay, so this is from a past IB exam. This question here is also from a past IB exam. Okay, you can tell from the formatting. So see if you can answer this question, and then we will end the video in 1 or 2 more slides. Which of the following is a derived unit? Okay, so hopefully you recognized that the mole, Kelvin, and ampere are all on that list of 7 fundamental units. Therefore, the only one left is a derived unit. That is the coulomb. That is the SI unit for electrical charge, and we will see that in IB Physics 2. Okay, so the last thing we're going to talk about is this chart right here. Okay, SI prefixes. And you might have seen this in your past science classes. SI prefixes are basically used to take really big numbers and to write them in a more simplified way. Here's what I mean. Okay, we have this chart here, and there's a lot of words on this chart like peta, tera, giga, mega, kilo, hecto, deca, deci, and so on. And there's numbers next to these things telling you the order of magnitude associated with those words. So, for example, kilo is next to the power, or is right next to 10 to the power 3, which is 1,000. Here's what that means. That means if I make, let's say, $1,000, or let's say, $1,000, that is the same as 1 kilo dollar. Now, I guess people don't talk like that, but that's just a simple example. So, in other words, you can use SI prefixes that are on this chart to write really big numbers in a really simplified way. If you read the text, what it says here, and you add this to your notes, what it says is, let's say you own a power plant, and let's say the power plant puts out 1,000,000 watts. Now, you could go around saying, hey, I have a 1,000,000-watt power plant, or you can look at the chart, 10 to the power 6 is 1,000,000, which is mega, and that's a capital M. So instead of saying 10 to the power 6 watts, or instead of saying 1,000,000 watts, you can just say 1 megawatt. So in other words, that capital M is a direct replacement for million. Okay, in other words, if I had 1,000 megawatts, that would be 1,000 million. That would be like a billion. Okay, that would be 10 to the power 9. So I could also write 1,000 megawatts as 1 gigawatt. If you don't know what a watt is, that's fine. That's not a big deal. Okay, you need to know these SI prefixes because we're going to be doing a lot of problems where I assume that you know these SI prefixes. And so if you're doing a physics problem and you have to do a unit conversion that we'll go over in the next video, you're expected to know these SI prefixes. Okay, so I would highly encourage you to dedicate these to memory. You don't need to do all of them, but I will tell you right now that the ones that you probably should know are probably, I'd say, everything between tera down to nano. It's not super common for you to see other ones, and you're actually given this chart on the IB exam, so you don't technically need to memorize all of them, but I would highly encourage you to do so that you don't have to spend the time looking up on assignments. Okay, so in the next video we will talk about how to do unit conversions with this chart. Okay, so please look over this chart and see if you can't memorize these values. If you have any questions, please let me know, and as always, I will see you guys in the next video.